Hey everybody. Today we're talking about the comparison test for series. The idea is pretty simple. If you have a series that's larger than some divergent series, it has to diverge too. And if it's smaller than some convergent series, it has to converge too. Let's be a bit more mathematical about that. So we're going to call the two series sigma an and sigma bn, and we're going to assume that they always have positive terms. And let's suppose that for every n, an is less than or equal to bn. So the terms of the an series are always smaller than the terms of the bn series. The comparison test says that if the sum of bn converges, then so does the sum of the an. And conversely, if the sum of an diverges, then so does the sum of the bn. So let's do a few examples. Problem 1. Does this series converge or diverge? Sum from n equals 3 to infinity, 1 over the square root of n minus 2. So I started at n equals 3 here. Remember that when we're testing convergence and divergence, the starting point doesn't matter. So here I'm noticing that this series looks a lot like 1 over the square root of n, which is a divergent p series. P in this case is 1/2. Moreover, this series that I have here with general term 1 over the square root of n minus 2 is actually larger than 1 over the square root of n, the general term for that p series I mentioned. How do I see that? I notice that when I go from the left to the right, from 1 over the square root of n minus 2 to 1 over the square root of n, I have made the denominator greater. And when I increase the denominator, I'm decreasing the overall fraction. So therefore, the 1 over the square root of n minus 2 is going to be greater than 1 over the square root of n. So we know that the sum of the 1 over the square root of n diverges. Therefore, the larger series, sum of 1 over the square root of n minus 2, must diverge as well by the comparison test. Problem 2. Determine whether this series converges or diverges. Sum from n equals 1 to infinity, n cosine squared n, over n to the fourth plus 3. So again, this is a series with positive terms. N is always greater than or equal to 1, and so n over n to the fourth plus 3 is positive. And then there's a square on the cosine, so that'll always be positive as well. Okay, so cosine squared is between 0 and 1. So when I take that out, I make the numerator larger. And then in the denominator, if I take out the plus 3, I've made the denominator smaller. That'll make the whole fraction larger. So overall, the general term n cosine squared n over n to the fourth plus 3 is less than or equal to n over n to the fourth, which is 1 over n cubed. Now, the sum of 1 over n cubed is going to converge. That's a p series with p equals 3. And therefore, since it's larger than the series we're interested in, that series has to converge as well. The sum n times cosine squared of n over n to the fourth plus 3 has to converge. One thing to watch out for. The comparison test has 2 bullet points. If the sum of bn converges, then the sum of an has to converge as well. And if the sum of an diverges, then the sum of bn has to diverge as well. There's 2 things that it does not say. Suppose that an is less than or equal to bn, as before. And now suppose that the sum of an converges. Well, the sum of bn could converge or diverge. That's a larger series. And so the fact that the sum of the smaller series is finite doesn't tell you anything about whether the sum of the larger series converges. Similarly, if the larger series diverges, you don't know anything about the smaller series. Could converge, could diverge. Here's an example. Sum n equals 1 to infinity, 1 over 3 to the n minus 1. So your first instinct, after a little bit of practice with the comparison test, is to compare this with 1 over 3 to the n. That's a convergent geometric series, r equals 1/3. However, 1 over 3 to the n minus 1 is actually greater than 1 over 3 to the n, because going from left to right, I make the denominator larger, which shrinks the fraction. And being greater than a convergent series doesn't tell you anything at all. We can't draw any conclusions yet about the sum from n equals 1 to infinity of 1 over 3 to the n minus 1. We need a more sophisticated technique.